Hi everyone. Uh, I hope you can hear me well. So we started this discussion measuring stars. So what we're trying to do here is to look at how we can take measurements, determine various physical properties of stars, how far away the star is, and how big it is, and the temperature on the surface, that kind of thing. So therefore, it would be very interesting. And this will be different from your usual measurement, instrumentation measurement techniques that you usually study in engineering and various other technical domains, right? Because this is astronomy, you are dealing with very big distances, um, and observations are kind of different, not direct. Okay. So that's why I thought this would be really interesting, because most of you guys are coming from a science mathematics background. So something in the same domain, and which is not highly technical, would be very interesting difference for you, right? So we looked at the parallax concept. I think you have already learned what it is and how interesting these measurements are. In order to measure the parallax angle of a star, it takes 6 months, you know. So this is the fascination about doing astronomy. And not only the distances, but the time scales are also very big, right? Whereas in your normal engineering and technical practice, you don't wait 6 months, right? Usually, right? But in astronomy, very interesting things happen. So you take the measurement of a star, take two photographs, 6 months apart, and you know the rest of the story, right? We looked at that. And then we looked at the parsec. Oh my God, the distance is huge. 10 to the 13 kilometers, like 10 trillion kilometers, right? That is kind of unit, right? In astronomy, astronomical measurements, right? Like meter or kilometer in normal engineering. And this is a simple equation. D is equal to 1 over p. P is the parallax angle. We looked at that, and some of you guys actually calculated the distance to the nearest star to the sun. That is Proxima Centauri. That's why it is called Proxima in the first place. And you got that answer, 4.24 light years away. This is really interesting. I'm sure most of you guys, you knew it from the references books, etc., that Proxima Centauri is 4.24 light years away. And this is how you calculate using parallax. So I think this will be like gap filling kind of thing, right? You knew something, but you really didn't know how it came about in the first place. Now you are filling those knowledge gaps. Now into this one, mathematics of scale of brightness. So let's talk about brightness of stars. Right? You have seen stars in the sky. Some stars are much brighter. Some even you have figured out, see the colors, red, blue, etc. Some are very faint. So this goes to very, very old ages in human history, to Hipparchus, right? Even that time they were like concerned about the brightness of stars, right? So back then they have invented some convention. Okay, let's use this convention to give numbers to stars, okay, based on their brightness. So look at these three bullets here on your screen. The first bullet, the first magnitude star, right, the first magnitude star. So we call some stars the first magnitude star, and some other stars we call second magnitude star, third magnitude star, like that. So we give stars what is called the magnitude. Actual magnitude is the brightness, how bright as you see it, right? Uh, According to the scale, if you know actual brightness, and if you look at the magnitude numbers given to these stars, right, our ancestors, without even going through some scientific measurements, right, now we know that the first magnitude star is 100 times brighter than sixth magnitude star. So if you take the magnitude of a star, right, and then add another 5 magnitudes, right, to that number, you get the second star, right? The difference between the two magnitudes is 5. And then if you actually measure the brightness of these two stars, you can see 100 times. 100 times. The difference, 5 magnitude difference is about 100 times brightness difference. Okay. The actual brightness is brightness, and the number we give to these stars is magnitude. Okay, because it's easy to use these numbers like magnitude 1, 2, 3, 4, like that, to start then talking about brightness. Okay. Now the 100 came because it's a nice number, right? But actual difference between two nearby magnitudes, say magnitude 1, 2, or 2, 3, 3, 4, or -1, -2, any two scales in magnitude, if you look at what sort of a difference in brightness it is, right, is about 2.512. 2.512, let's say 2.5. So if you see one star, let's say A, and there's another star B, B is 2.5 times brighter, right? B is 2.5 times brighter than A, which means B is, the magnitude of, let's say, okay, let's stick to the same example, 2.5 times brighter than A. So who is brighter? B. Okay, B is brighter. So let me go. This is kind of confusing, so therefore I want to write it like A, right, and B. So the brightness, let me call it, say this is B, brightness, this is magnitude M. Right, let's say the brightness of A is X, and the brightness of B is 2.5 times X. So this is what I'm trying to say, right? B is 2.5 times brighter than A. Now, let us call the magnitude of A is, say, 5. Right? Now, B is 2.5 times more bright. So, therefore, you might think that the brightness of B in terms of magnitude, right? If you want to put the magnitude, you might think it is 6, right? But it's not 6. 6 is wrong. It's 4. It goes the other way around. So no argument, scientific argument. This is what it is right from the beginning. Okay. When the brightness increases, the magnitude drops. That's how the numbers were assigned. So magnitude 4 star, magnitude 4 star is brighter than magnitude 5 star. Okay. 4 star is brighter than 5 star, and the difference is 2.5. Please keep that in mind. So the third bullet is nothing new. Magnitude difference of 5 corresponds to a factor of 100 in brightness. So if you just punch in 2.512 to the power 5, this is approximately 100. Okay, just do it by hand and you will figure that out. So it's easy to remember, right? There's a scale called magnitude, and it goes to Hipparchus time. There's no scientific basis. Therefore, we are not going to change it or discard it. We just use it as it is, kind of legacy, right? Just for information and knowledge, we teach it and you learn it. It's about brightness of stars. And if you say there's one star which is 2.5 times more brighter than the other one, then its magnitude is one less than the dimmer star, okay? Less brighter star. So less brighter means higher number in magnitude. So keep that in mind. Let me show you this scale, right? If you put known objects in the sky starting from the sun is the brightest, then the full moon, then you have Venus, you have Sirius, right? I'm sure some of you may have seen Sirius in the evening twilight or before sunrise, right? Dusk sky, a very bright star. And then you have naked eye limit, a binocular limit, and then you need large telescopes to see other faint objects. And then you go to Hubble Space Telescope above the atmosphere, free of any light pollution, free of any clouds or anything. You can see much more clearer. So you can see much farther, right? So that is the entire spectrum. And if we start from naked eye limit, right, that's about +6, magnitude-wise +6. Again, there's no scientific basis, there's no definition or equations here to calculate magnitude. Just remember these numbers, okay? And when you go up in brightness, you can see the numbers, right, getting small and small. Eventually you get to negative also. Sirius is much brighter, but the magnitude is -1.4. Venus is brighter than Sirius and it's 4.4. Okay, so you can see this is 1.4 to 4.4, three magnitudes, three magnitude difference. So this means if you want to calculate how bright the Venus is, right, how bright the Venus is compared with Sirius. So how many Sirius is Venus? The answer is 2.5 to the power this minus this magnitude, right? So 4.4 minus 1.4 is 3. 2.5 to the power 3. So the Venus is this many times brighter than Sirius. Okay. Now full moon is 12.6. Sun is -26.7, right? And you can take this scale and do little calculations, right? For example, Pluto, right? Pluto is plus 15.1. And it is not visible to the naked eye because naked eye limit is +6. If I ask you, if you can put so many Plutos together, how many Plutos do you need to put them together so that it makes visible to the naked eye? How many Plutos? Again, the same calculation, 2.5 to the power of this difference, 15.1 minus 6. So that many Plutos are required, right? To make it barely visible, barely visible. So take this and take this as a little homework, right? Do a little few calculations just for fascination. Okay, right. I will put up a few questions into a assignment and upload to the Moodle. So you can download the assignment and submit your answers. Okay, simple questions. And if you go into Hubble Space Telescope, right? That's plus 30. You can see it over here, plus 30. So we have no idea what this plus 30 means. Okay. In order to get some idea what this plus 30 means, how far or how sharp the vision is of Hubble Space Telescope, in order to convince yourself, one way is to design a small exercise. Let's say your binocular limit is, naked eye limit is plus 6. 6 to 30 is 24 steps. So 2.5 to the 24, just calculate it. Just calculate it. 2.5 into 24 to the power 24, right? So the Hubble Space Telescope can see, right, that many faintish object, right? Let's say there's some object that you can see barely. So if you look at that, if you stare at that in a very clear sky, you like see it and you don't see it, right? It's something like that, on the verge of seeing it. So it's, you barely see it, right? Now if you reduce this brightness by this factor 2 to the 5 to the power 30, that is the limit of Hubble Space Telescope. So Hubble can see that much faintish objects. Okay, so I think these numbers are interesting, right? To know, because I really am fascinated to understand things by numbers rather than concepts. Okay, and then when we want to understand certain thing in the universe, in this world, the best way is to relate it to something that we know of, something we have experience of, and then get a multiplier, right? Or device like that. So then we can at least try to reach to that reality, right? To understand what it really is. Now, this is a photograph everybody has seen. What is it? Can somebody tell me what this is? What is this photograph? This is not a painting or any artistic illustration. This is an actual photograph. It's a very famous photograph. Every astronomy book, general astronomy book has it. No idea? Can somebody unmute and tell everybody what this is? Unbelievable. There are a few people who have done astronomy uh, before this course. They might know this. This is what is called the Pleiades star cluster. Pleiades star cluster, more commonly known as in Sinhala Hadinataru. You have heard that Haddinataru. Haddinat means 7 stars, right? So you can actually count. There's about 7, right? Depending on how far you want to count, it can be 7 or 70 or 700. But the brightest ones 1, 2, 3, 4, 5, 6, roughly about 7, right? So these numbers are the new things here. These are the actual magnitude of these stars. So if you go to the brightest one, probably over here, that's about 2.84, and then the other ones are like I don't know why this is not marked anyway. Um, so not the major stars of the Pleiades, but the other ones are also marked. You can see it over here, right? And this is plus 8.53, right? When the number increases, it becomes much more faint, right? Okay. So now we are getting a bit serious from here. Apparent magnitude and absolute magnitude. So then this becomes a bit more scientific now, but I'm sure you will like it. Now we know what magnitude is. Magnitude is actually the brightness, right? Brightness in a different scale, okay? And not a scientific scale. But as you know, uh, how bright or how faint a star is depends on how far it is, right? So nearer the star looks more brighter, and farther away the star is, it looks much more dimmer, right? So therefore, with this variable, the distance, it's very hard for you to compare stars, right, in terms of brightness. So apparent and absolute comes on that scenario. Absolute means independent kind of thing, right? So all the stars, when you say absolute magnitude, which means that is the perfectly compared magnitude. So in that case, you can compare how bright a star is compared with another star, right? When you compare the absolute magnitudes. But if you just forget the distance, forget about the distance, right? We don't know the distance. We don't worry about the distance. As you see it, you give the magnitude. Hipparchus time and up until now, right, it's a legacy scale. It's not going to change. The numbers are actually apparent magnitudes, as we see, okay? For example, our sun, the star, is very, very bright, but there are much more brighter stars out there. They don't look so bright, not as bright as our sun, because they're much farther away. That's why. Not that they are dimmer, okay? The apparent magnitude is a measure of a star's apparent brightness as seen from the Earth. You understand that? The magnitude depends on the distance to the sun, to the star rather. Then the absolute magnitude, so this is the new thing, right? Is the apparent magnitude a star would have if it were located exactly 10 parsecs from the Earth. There you are. Now you can't have stars here and there, nearer, farther. Everybody has to be at the same distance. So you ask every star to line up 10 parsecs away from us, from the Earth. Everybody. You ask our sun also to move out to 10 parsecs away. And all the other stars, Proxima Centauri and other things, to line up at 10 parsecs away. Okay, some stars will have to come forward, some have to go back. Okay, they make the line. Now you measure the apparent magnitude. You always measure apparent, right? Because as you see it, you have to line them up and then give the numbers. So whatever number you give when the star is at 10 parsecs away is the absolute magnitude. Absolute magnitude. Now, if you calculate the absolute magnitude and the apparent magnitude of the sun, our star. Of course, you know the apparent magnitude, you saw it earlier, 26.7 minus. That's the apparent magnitude of the sun. But you know that it's just 150 million kilometers away from us, right? It got to be very faint star, right? If you put it 10 parsecs away. So if you really do that, bring the sun 10 parsecs away, and it will look like a faint star. And the absolute magnitude of sun, or the apparent magnitude when you have the sun 10 parsecs away, is only 4.8. 4.8. Okay. So 4.8. If you go back and see something 4.8 similar to this one, Venus is minus 4.4. Maybe we can compare our sun to Venus. If you bring the sun to 10 parsecs away, 10 parsecs away, the sun will look like Venus. If you have seen Venus, you know what I'm talking about, right? This is another approach for you to understand how long a parsec is, right? The sun, the bright mighty sun, you make it like Venus, still bright, okay, but just a blob in the sky. So when you move the sun to 10 parsecs, so you understand that then sun is not a mighty object, right? After all, it's just a normal star, right? There are so many other stars like that in the universe. Now we are getting a little bit more serious about this scientific aspect, right? First, look at this equation. Everybody has seen inverse square law, right, from your A level. Okay, so this is therefore very familiar thing to you. I don't expect anybody to have any problem with this kind of laws, right? The gravity, radiation, etc. You have seen these kind of equations. So what is it here in astronomy? B is equal to L over 4 pi d square. When you see 4 pi, again, you see this is a area of a sphere and all, right? So everything is very, very familiar to you. So this capital L on the right-hand side is star's luminosity. So this is another new word for luminosity, right? Earlier we discussed about brightness and the magnitude, which is also the brightness on different scale, and then the luminosity. So you might tend to believe these are the same things, right? Eventually, but it's a bit different. Luminosity means, as you can see it over here, in watts, the total power output. The total power output. Let's say it's a light. In your houses, you have 15-watt LED or 100-watt incandescent, like that. Okay, the total energy output. Okay, so that is L, total energy, divided by 4 pi d square. So d is distance to star in meters, distance to star. Now if you look at our sun, we know the distance to the sun, right? 150 million kilometers. If you know the total energy output from the sun, divided by 4 pi d square, the distance, you get B. B is the apparent brightness of a star. Apparent brightness of a star in watts per square meter. So this is much more scientific now, right? That is the essential difference here. So it's apparent. It's apparent. It depends on the distance. This d is the distance, right? Now, if you look at this equation, B is the apparent brightness. This is something you can measure. Brightness, how bright a star is. There are techniques to measure brightness of objects that you see, right? It is measurable quantity. Distance, sometimes, yeah, you can measure the distance also using parallax and other methods, right? So if you know these two, you can calculate L, total output energy, how much energy is being emitted. Okay, so that is why I call this, title this lecture as Measuring Stars. Now we are going to look at fundamental equations, laws of nature, and then figure out what are the variables and which of these variables can be measured, and then other variables can be determined. Okay. So in this illustration, you can see, if you are closer to star, distance 1, distance 2, distance 3, like that, this is inverse square, right? When you move out of a star by a factor of 2, right, then your luminosity drops by a factor of 4, right? And if you move out of a star 3 times, the luminosity, or the actual brightness that you measure, drops by a factor of 9, right? So that is inverse square law. So keep that in mind. That is an interesting equation. Now, if you write down the luminosity equation for our sun, for the sun, right? You give it this encircle dot subscript every time you write an equation for our sun. It's a special case, right? For sun, you write this equation is not just B subscript encircle dot. That means the luminosity, the apparent brightness of the sun. So L encircle dot means total power output of the sun. Okay, like that. So keep that as a reference equation. And then you write the same equation for any other star. And then divide. Right? Once you divide, you get this equation. So this is a relative equation. Relative equation, which means what is the total power output of that star, right, as a factor of the total power output of the sun. So we are comparing total power output, right, the two power outputs. And on the right hand side, you can see the distance, right, and the apparent brightness, B over B sun and D over D sun. Okay, so this equation is not new equation. It's a relative or ratio between the same quantity, right, and that of the sun. So we quite often use this one to calculate certain parameters of other stars as a factor of the same parameter of the sun. So for nearby stars, okay, the distances can be measured using parallax method. Nearby stars, as you know, if you try to measure the distance to a very far away star, the angle, parallax angle, will be very small. So as you know, when you measure very small quantities, your measurement error will be significant. And at some point, your error will be bigger compared with the measurement, actual physical quantity that you measure. And at that point, right, or before that, you have to discard that method and say, okay, we can't use this method for that kind of measurements because we call it signal to noise ratio. The noise is significant, okay, compared with the actual physical quantity that you measure. So as a result of this equation, the application of this equation, by now we have found there are a lot of so many stars out there that are much more luminous than the sun, much more luminous than sun, big and bright, okay. Now I want to turn into this content, the spectrum. So in all these all three figures here, you can see the wavelength in nanometers, right? Like starting from around 400 to about 700 is the optical or visible light. Before 500 is a very short wavelength, not visible, ultraviolet and other things. And on the red side, on the other side, after red, it is infrared, again not visible, and all the other gamma, X, etc. Okay, this is the entire electromagnetic spectrum. From here to here is the visible. So everything that we see in this discussion is visible light, okay, visible things. Now, compared with that one, with that background, you can measure stars' light emission, right? When I say light, it doesn't have to be optical. Let's say starting from very low wavelengths to very high wavelengths, right? If you can measure and plot it, how much gamma rays emitted by that particular star, how much blue light, how much red light, how much yellow, how much infrared, how much ultraviolet, how much X, like that, then you can actually plot this curve. You will get something like this, depending on the temperature of that star. So curves are like that. For some stars, it will be like this. Some stars, it will be like that. Some stars, it will be like that. So every star will show a particular emission curve with respect to the visible part of the spectrum. Okay, I think you are following what I'm trying to explain here. This curve is the emission curve of the star, whatever star. Some stars are like that, some stars are like that, some stars are like that. But there's a particular pattern as to why a star emits like that, while another one is emitting like that, and yet another one is emitting like that, right? So this goes to very old ages, like Wien's law, which says if you observe a light source like a star, say for example, he proposed this equation: lambda max is equal to 0.0029, right? Km over T. So there so this is in Kelvin, right? The temperature of the star. So this is not necessarily for stars, for any black body which is emitting electromagnetic radiation. When you draw the curve, like that, you will always see that this is like a convex problem, right? So you always get one peak, just one peak. You don't see two peaks, three peaks. It's always like this. It's like in mathematics or in engineering, we call maxima, local or global maximum. Global maximum. You always get one and only one peak. And the wavelength of that peak is given by this equation. And it is inversely proportional to the temperature. Okay, inversely proportional to the temperature, which means when if there is a very hot star, very hot star, very high temperature, this wavelength is very small, like this. And if there's a star which is not that hot, right? There are no stars which are that are not hot. Okay, so in relative terms, there are some stars like cooler stars. Their temperature is not that high, so therefore their maximum wavelength is high. So like over here. So this emission curve, the moment you look at it, you see that this particular emission curve is actually coming from a relatively cool star, right? Whereas this wavelength, this emission curve is of a very hot star. You can immediately figure that out. In fact, if you have sophisticated measurement apparatus to measure stars spectrum, emission spectrum, that of course we have it, right? You can actually create or generate this waveform, this blackbody radiation curve, and figure out the peak, maximum lambda. The moment you know that, you can put it over here and calculate capital T. Okay, so that is how you measure the temperature of a star using the spectrum. So this is another illustration of the emission, light emission from a star. So you can see the visible spectrum again over here, starting from 400 to about 700. This is the visible part. Then you see the different filters, U, B, V, like that, right? This area in astronomy is called photometry. Photometry, you measure photons, you measure light. So, in order to generate a curve in engineering, you know how you do that. So what you do is you have the graph, right? You get the measurements like that, right? And then draw the line, right? That's how you do. Same here. But if you want to measure how much blue light is there, you need to have a blue filter. If you want to know how much red is there, you need to have a red filter. How much green filter. Like that. So there are a range of filters that you are using in your imaging equipment, and you measure the emission. You don't have to be absolute. You have to take absolute measurement. No. If it is a relative measurement, that's good enough, because you are going to get the ratio and then plot it. Okay. How much blue versus red, and like that. So when you see this ratio, you can easily figure that out, which one is this graph. Okay. You don't need to have so many samples in order to draw this curve. Right. So we call it color ratios. Color ratios. You really don't need to quantify different colors, how much light you are getting from that. But nowadays technology is there to actually measure gamma rays one by one, gamma rays one by one. And if you go to Stanford, you can see there's a small museum in campus. There is an apparatus. I don't know how it really works, but it it is a photon detector. It's a photon detector. Uh, uh, I think it's gamma ray kind of thing, right? Coming from the sun or maybe cosmic radiation. When that enters into the apparatus, they amplify it and then eventually get a little signal, right? Little signal and a little LED blinks. Okay. It's not a fake thing, it's a really genuine apparatus. So when you keep an eye on it, it was like 10-15 minutes. If you stay there, you get blinks couple of blinks. Everyone it's a gamma ray or something coming from the sun. So that was a long time ago. I kind of forgotten what it really is. um, it might be gravity wave or something, some very peculiar, unusual photon, right? Or some other subatomic particle that you don't really see on the Earth. It has to come from either the sun or the cosmos somewhere, right? So the technology is there to measure, but if you just look at what you really want to construct this graph is the color ratios. You only need to know the ratios. If you see the graphs over here, is a peculiar ratio between blue and red. If you see here, blue is small, red is high. Here they are equal kind of. Here the opposite, right? So then you know which side you are with respect to the peak, the left side or the right side. So immediately you know you are on the left side, so it should be a cooler star. When you know you are right side, you know it's a hotter star. It's like that. It's kind of easy to figure that out. So with couple of measurements, you can uh, confidently track the curve. So that is how astronomers measure or deduce the temperatures of stars. So then they have gone far beyond that point. Here, what you see is the color ratios, the violet versus blue, right? Violet versus blue. They are very closely apart, right? Violet and blue. If you just take that ratio and the surface temperature, you calculate the surface temperature, you can draw this curve. This is Bellatrix, and this is our sun, Aldebaran. Aldebaran is red. Red means, it's not that hot, right? If you go back, you can see that. Red is over here, right? So any star which has its peak right over here, red, or after red, right? You will always see it like red. Okay, always see it like red, and you know it's a cooler star. It's a cooler star. So Aldebaran is red, so it's a cooler star. It's cooler than the sun. And if you look at Bellatrix, it's a kind of blue. It's a hot star. And here you can see this table, some stars that you know of. Bellatrix, Regulus, Sirius. Sirius is here again. Sirius is the brightest star in the night sky, and it's the main star in Canis Major, right? Altair is a very bright star. Aldebaran, Betelgeuse, they all. Now you can see sun. is just another star, right? Among the other stars, right? You can see these numbers. Bellatrix is 21,000 Kelvin on the surface, right? This is surface temperature, mind you. It's not the core or anywhere, it's only the surface, because we take the measurements of the surface. So whatever we determine, it's of the surface, right? And among the others, sun is pretty normal, 5,800 Kelvin. That's the surface temperature. I think you have heard it, like 6,000, right? So pretty close, 5,800. And other stars like Aldebaran and Betelgeuse are cooler. And these two stars are also kind of famous. Aldebaran is from the Taurus constellation, and Betelgeuse is from Orion, right? These are also very familiar, the star patterns. And this is the color ratio, violet versus blue, and blue versus ultraviolet, right? So see, with these two ratios, you can track that. So because is that close, right? And if you look at the color that you see, right, naked eye, it's kind of difficult to figure that out. But if you have a really clear sky, dark sky, you can actually detect the color. Bellatrix is like blue because it's a hot star, right? If you look at, if you go back, pedal back to this one, here you can see when you are really hot, your peak is closer to blue, right? It can be ultraviolet, but we can't see it. But next to that is visible part is blue. You will see the bluish color. So this is a very hot star, 21,000 Kelvin, Bellatrix in Orion, right? It's blue. You can see the blue star in Orion. Figure that out, Bellatrix. Okay, where Bellatrix is. Which star in Orion is Bellatrix? And it's blue color. And in the same constellation, Orion, you see another one, Betelgeuse, right, which is only 3,500 Kelvin, same constellation, right, and it's red color, right? You can see same constellation, Bellatrix and Betelgeuse. So why don't you go out in a clear sky, check the star chart? I will ask probably Shake to come and talk to you next week if he's free, and talk to you about star charts, telescopes, and observations, right? He will give you a little assignment to map either constellations or the moon and sketch it. That will be, I think, you will like it. Part of the course, I want you to remember some of these names, okay? These are good names, no? Now we go into the fully fledged spectrum. Fully fledged spectrum. Not just ratios of different colors, but if you do a very comprehensive series of measurements, right, you can do that. And this is the entire spectrum of different stars. If you generate the spectrum of a 35,000 Kelvin star, you will see it like this. You will see it like this. Don't worry about these arrows coming from the top and the bottom. Don't worry about that. And 22,000 Kelvin, 16,000 Kelvin, 10,000 Kelvin, like that, down to about 3,500 Kelvin, right? You will see very subtle differences are there, but the subtle differences is enough to differentiate between them. So where is our star? I think it's over here. It's G2, right? The hotter stars are um, class O over here, and the cooler ones are M stars, M2, M0, like that. So our sun is right in the middle, almost. It's a G2 class, and it's like between 5,600 Kelvin to 5,900 Kelvin. Actually, it's about 5,800 Kelvin over here. Okay. So now, what are these arrows over here. You can see something you have seen, right? You know of. You can see hydrogen, helium, magnesium, like that, iron, etc. Okay, and titanium, sodium, like that. So, and there you can see black lines here, black lines. Okay, black means absorption. Black means absorption. So for some reason, say for example, K5 star, this one, 4400 Kelvin star, it emits all the light, right, from blue to red. But somebody has taken this particular wavelength. Somebody has absorbed that wavelength. Who is that guy? It's sodium. If sodium is there, it will absorb this wavelength, right? But it will not happen everywhere. So based on the temperature, of course, right? So sodium can present there or sodium cannot present there, right? So if sodium is there and if the temperature is cool enough for it to survive, and you will see this dark line. All the dark lines are here because of this additional material in the outer surface of the star, and they absorb those particular wavelengths. So once you know that, we use this spectrum in order to determine what are the other materials, other elements in that particular star, in the atmosphere, whether sodium is there, whether calcium is there, whether manganese is there. Just by looking at the absorption lines, you can find it out. That is another measurement technique, right? Look at the emission spectrum of a star and find out the absorption lines, and compare the absorption lines, right, of other elements that we know of, from hydrogen to very heavy elements like gold, platinum, etc. There are standard emission patterns peculiar or unique to these elements. So if you see that particular pattern in an emission spectrum, you can conclude that, okay, this particular material is there on that sun, okay, on that star. So these are the spectral types, the classes, right? I just mentioned O, B, A, F, G, K, M. These are the hottest ones, right? O, coolest ones, cooler guys are here. M. G is slightly towards the lower side from the center. Our sun is G. Yeah, I think everything is there. From O to M, the temperature decreases. So temperature decreases from here to here. Subclasses. Now, you have already heard that sun is G2. So it is the second class of the G type. So there are other classes, G0, G1, G2, like that. Okay. If you take B, for example, B0, B1, there are a lot of subclasses. It's a very complicated thing. It's very high resolution kind of distribution. Okay. Right. I think it's time for a little break, about 10 minutes, right? Let's get a little break. I'll be back in about 10 minutes.